Now we're entering the third part of our session. It's a long session. Yeah, it's a long session, but really interesting so far. And now we have a really interesting part when the future leading researchers will take the stage. And they will do it quite rapidly. We wanted to go for the full precise because I'm precise doctor. We like the Pachakucha style, but of course in Israel we have to bend the rules a bit. So it will be 5 minutes and not exactly 20 seconds per slide. Come on, why do we need to do that? Okay, but 5 minutes. I will be punctual on the 5 minutes.
Okay.
Take into account all presenters out there, and the rules are like that: 5 minutes, 5 minutes, 5 minutes times 6, and then we have 3 commentary sessions by our distinguished guests. Only them, only they will respond to your presentations. 1, 2, 3. This is because you hear us all the time, right? You will hear them. Each one of you, you decide the order, will comment on 3 of you, on 6 of the presentations together. You generate a discussion. You can ask questions, you can do whatever you want. The floor is yours for 5 minutes. So this is a really clear. We can start immediately. I do fast presentations also of the speakers. We start with Coral. Coral, welcome. Coral Hamokorin is an architect and an urban planner. She's currently pursuing a PhD at the Computational Design and Machine Learning Lab. Yes, sounds familiar because Guy is leading it under the supervision of Assistant Professor Guy Ostern and co-supervised by Professor Yasha Grobman. Welcome, Coral.
Hello, everyone. To be honest, it's a big challenge to present my research in 5 minutes, but I will try. So, my research focuses on leveraging machine learning for automated urban analysis. Why do we need to upgrade our urban analysis methods? As cities grow rapidly and become more complex, traditional analysis methods are no longer sufficient. That's why we are offering computational machine learning framework that utilize both supervised and unsupervised techniques, integrating various open data sources, allowing it to work in place where private or governmental data is not available. We offer in a multi-scale method that enhances optimization and creates spatial synthesis based on urban insight. By analyzing 3 urban scales, building, block, and neighborhood, using a bottom-up perspective. So in the first stage of the research, we start from the building scale with the aim of using its insight for the next scale. We choose to analyze the building topology using available satellite imagery with a vision-based model because satellite imagery is the most accessible data source for global urban analysis. We use a basic machine learning workflow, and then we develop our tagging. We tagged building in 8 neighborhoods in 2 different cities. Next, we choose the Fester's CNN model due to its ability to perform detection and classification. We achieved a 70% accuracy. The result was stronger, especially considering the limitation of the small data set. Here we can see the model result on fully automated mapping compared to the manual mapping results. The strong similarity between the 2 maps highlight the model high potential for automatically identify various urban environment parameters. Still, this is a local method. Building tagging is context specific. So in the next stage, we move to the block scale. The goal is to develop a method that can be applied in a wide variety of cities. For this purpose, we developed a framework that combines 3 methods: using heuristic algorithms, supervised learning based on insights from the building scale, and unsupervised learning that analyze large amount of block information and performs clustering. For block extraction, we generate polygon based on filtering categories, such as row type and number of buildings, using open data from OpenStreetMap. Then, for each polygon, we analyze the building topology it contains. Next, we apply heuristic algorithms to analyze various block parameters automatically, such as block number of building, block area, average distance between building, average distance to the road, etc. And now for each block, we have all the information, like road types, building topology, and all other criteria. Then we perform data analysis and processing, check each parameter distribution, create a normal distribution, and examine the relationship between parameters. And next, we took all this information to our unsupervised canvas model, and this is our final clustering model. If we zoom in on each block, we can see the classification of cluster number 5 at the top and cluster number 3 at the bottom. We see that in each cluster, there is similarity in the building and road type and also in the structure. And actually, this is the current state of the research right now. In terms of research limitation, we are dealing with generalization issues specifically in the supervised learning method because every city in the world has diverse criteria, and we hope to solve it by developing a self-supervised method. This research contribution has the potential to empower real-time, complex, and compressive urban analysis for better decision-making, and to generate volumes of urban data in underdeveloped areas.
More seconds.
You can sell it to
How we
somebody.
use them? Maybe we use them to introduce the next speaker. Elam Sklar is an architect and doctoral researcher. Sounds familiar, Elam Sklar, okay. At the Environmental Performance and Design Lab. His PhD is supervised by myself and co-supervised by Professor Bigetuz. Here we go.
Long time no see. Good afternoon, everyone. Thank you for being here today. My name is Elam, and I'm pleased to present my PhD research, which proposed the machine learning approach to optimize building envelopes in the early design stages, integrating urban, building, and environmental considerations. Let me start by painting a familiar scene, at least for those of us from Israel. You're walking down the street in Tel Aviv, late afternoon, in the middle of the summer. The heat is coming from everywhere. You look for a relief, maybe some shade under a balcony. But even there, the air feels thick and still. The building around you seems to radiate heat straight onto your skin. Even in the shade, there is no real comfort. Our cities are getting hotter, and it is not only because of climate change. The way we design them, the shape of our building, the form and the materiality directly affect the urban climate. This doesn't just lead to higher energy use. It also reduces our thermal comfort. And that's not a small issue, because the livability of our cities depends on our ability to keep living in them. The building envelope, walls, roof, facade, is where architecture meets the environment. It controls how heat, light, air, and wind move in and out, shaping our indoor comfort, but it doesn't stop there. It also reflects and radiates and light back into the surrounding. Its impact can be divided into three main areas. First, the indoor environment. Second, how the envelope affects energy balance and carbon emission. And third, the influence it has on the outdoor comfort in the surrounding space. All of those impacts are shaped by a key design variable of the envelope, its composition, morphology, and materiality. In today's architecture workflow, environmental consideration often comes at the end. By then, most of the envelope key features have already been defined. If we could address the environmental aspects of the envelope early in the design process, we could avoid creating problems that are much harder to fix later. But today, evaluating those factors is still too computationally intensive to do at this stage. That's the core question of my research. How can we evaluate and compare building envelopes early in the process? across multiple environmental dimensions without slowing down design. That's where new technology comes. By using machine learning, we can enable fast prediction that support better decisions right when they matter the most. To generate those fast predictions, we'll train three-dimensional convolutional neural network. But before we can do that, we first need to prepare the trained data set. The data set will begin with generating voxel geometry. It will include a mix of building typologies, urban scenarios, and 5 different envelope types: opaque, transparent with shading, greenery, and PV. This diversity is essential for creating a broad data set and avoiding overfitting. After generating the geometry, we'll use geometry encoding and envelope clustering to reduce the computational intensity. Next, we'll perform an environmental evaluation integrating the geometry with climate data to simulate how different envelope components affect the performance. Those simulations will cover indoor and outdoor thermal comfort, operational and energy use, embodied carbon, and daylight conditions. Once the dataset is complete, the fully processed envelope geometry will serve as the input, and the simulated environment result will be used as an output. Finally, the result will be processed and optimized using multi-objective optimization algorithm to identify the parameter form, highlighting the best trade-off between competing performance goals. Okay, I'm missing a slide, but sorry. Take that out from my time.
Okay. You have one more minute. It's fine. That's so nice. Yeah.
Okay. To emphasize the importance of understanding the complex environmental impact of the building envelope with specific urban and climatic context, especially at the early design stages, we conducted a preliminary study. It assessed how different levels of greenery cover affect both energy performance and outdoor thermal comfort. Interestingly, we found that in certain urban scenarios within Tel Aviv climate, partial implementation of greenery actually performs better than full cover. And now that's it. And thank you so much for your attention and for your thinking today. And remember, the envelope.
Okay, Roy Yosifov, please take a stand. You have fans here. Nice. You pay them? Okay. He's a practicing architect and a researcher at the Architectural Visual Perception Lab. His research is supervised by Professor Daphna Fischer-Wisma, and was supervised by Assistant Professor Guy Ostern. Good luck.
Thank you. Yeah. So, my name is Ray Yosifov. I'm an architect and researcher in the Architectural Visual Perception Lab. It's led by Daphne Fischer-Wisma. I'm excited to be here and present this project, which is a collaboration with Dr. Guy Ostern, Professor Guy Ostern, sorry, from the CDML lab. It's called Urban Spatial Openness Index in Machine Learning, predicting spatial openness of large scale urban fabrics using convolutional neural networks. So here we can see 3 different morphologies, all have the same exact built volume, but they generate different spatial experiences and have different perceived densities. At the ADP lab, we developed 3D simulation models that analyze visibility and spatial qualities across different scales, which help decision-making in regard to spatial openness and perceived density. Today, I'll talk about the USOI, or Urban Spatial Openness Index. It's a ray testing model that uses rays in grasshopper and rhino to evaluate the spatial openness in analysis points across the city. Its score for each viewpoint is defined as the accumulated length of line of sight of all sample points. The results of the USOI are then visualized as heat maps, where brighter color indicates higher spatial openness and lower perceived density. Every point is unoccupied by a building is measured, such as streets, parks, and courtyard. Each pixel of the image represents a 5 by 5 meter area and is assigned a value based on the USOI measurements. In Tel Aviv alone, there are around 1 million analysis points, which is a problem because in such a scale, raycasting analysis is computationally intensive. So we hope that to utilize a machine learning model to allow possible real-time analysis in such scale. So we used a unit convolutional neural network. The unit is a proven model widely used for image segmentation tasks. The idea was simple: to take building height maps, which are easily generated from 3D models, and compare them to the USI measurements, which we did in our script. So the idea was to take those images and train the model. And once the model is trained, we hope that we would be able to input a height map, which again is very easily generated, and the output, the special openness map of the region. So to do this, we have to create a data set. And we did it. We collected data from different cities covering 500 square kilometers and around 15 million analysis points. And now we can see the results. So the performance was very encouraging. Here we can see the prediction results of urban fires in the center compared to the actual measurements done by the raycasting model. The metric we used was mean absolute error, which measured the difference between the predicted pixel and the actual one. And the results were really good, around 2% in most cases, but some cities were harder to predict than others. Now, when we look at an entire city, you can see that the raycasting models took around 10 hours to create this analysis, and the unit model did it in 20 seconds. And the results were actually quite good. Most of the results are between 0 to 5% difference. So, to summarize this short presentation, the unit model could effectively predict special openness of urban fabrics with ample accuracy on a macro scale, with prediction time blocking from hours to seconds. We are working on developing this model to include vegetation and topography, which are also crucial to this kind of analysis, and to further research the USI values and associated urban morphologies across different case studies, and maybe considering other potential use cases like the sky view factor, which might be similar. So thank you. And finally, if you want to know more about it, I'm happy to share that our paper was accepted 2 days ago to the Computers, Environment, and Urban System Journal, so you can read all about it, or talk to me, Guy, or David here. So thank you.
Thank you all for keeping time. Very good. Now we have Naga Manafugada. Also looks familiar. He's an architect and data science expert. He's currently undertaking his PhD research at our lab, the Environmental Performance and Design Lab, under my supervision. Thank you.
Hello everyone. Today I'll be presenting the need and role of urban microclimate meta models, the surrogate models, so-called, for next generation building energy modeling. So we all know that building energy modeling tools are being largely employed for making informed design decisions. However, and these design decisions are important for promoting energy savings as well as without compromising on the thermal and visual comfort. Notably, these insights are questionable in the urban context, but why? When we look at this hypothetical urban block model with wind speed of 5 meters per second facing from the south direction, usually we will notice a low wind speeds on the central building, south facade of the central building, right? However, if you look at the building energy modeling tools, that is not accounted. Why? Basically, they consider the contextual urban elements, is it a building or a tree? It doesn't account its impact on microclimate. They are just the shading objects. So several such less known assumptions are made by a lot of building energy modeling tools. So we have accumulated them and we have a paper. If you're interested, you can go through it. Now the question is, so can we consider the microclimate impacts? From theoretical perspective, we have CFD-based urban microclimate modeling tools, which can actually generate phase-specific microclimate data and supply it to the building energy modeling tools. However, we have two major limitations. The first major limitation, like environment kind of models, can generate this data and building energy modeling tools will accept them, but not the other way around. That means the heat data from the building energy modeling tools is not accepted by the environment. The second major problem with all the CFD models is the time. If your building energy modeling tools can take seconds to minutes per simulation step, CFD-based models take hours for one step of simulation. So to overcome this limitation, we have used the simulation data from urban microclimate models and then deep learning expertise to generate this urban microclimate meta model. So the model which we just created for the Tel Aviv actually has shown a very good performance. For air temperature, almost error of 0.6 degrees Celsius. For relative humidity, it's only 5%, and wind speed of 1.3 meters per second. So how this meta model works? So for any given model, block model that you generate, you can actually create the Ladybug using Ladybug tools. You can create the energy model, and we have this custom model that can generate a Python API that enables the data exchange between the building energy model, Honeybee, and the meta model. Then we have another set of components which generate the predictors for specific block model you have given. Now, once you start the simulation, the data from the building energy modeling tools, like surface temperature, forcing climate data, which is used from the EPW file, and the predictors data is supplied to the meta model. From the meta model, each step, the data goes back, that is specifically the phase-specific microclimate data. Beyond actually generating the urban microclimate meta model and integrated building energy modeling workflow, we are actually we have created a workflow, advanced workflow that can enable us to get a representative urban block models and typical climate days so that you can generate a lot of diverse metadata that can help us to do machine learning models. The major USP of this project is the predictors that can characterize the complex urban geometry for every point. And that can be decoded by the custom deep learning architecture we have created. Although we would like to demonstrate this kind of things, we are waiting for our publication to go ahead. And thank you so much.
You have done that. Very good. I want to welcome our guests from University of Cincinnati. Feel free to join us to sit. They will be with us, I guess, for the next 20 minutes. So we are in the middle of a Pachacucha session of research on urban environmental intelligence. Very interesting. I think relevant for Cincinnati as well, I guess. And you are welcome to join and sit, please. There are spaces here. So we have two more presentations in the Pachacucha, and then we will have some commentaries by three international guests. Yes, so yeah, I would like to invite Sivan Sharabi. Sivan Sharabi holds a bachelor's degree in marine biology and biotechnology. She's currently a master's researcher at the Big Data in Architecture Research Lab, supervised by Assistant Professor Oral Alexandrovich.
Hi, hello everyone. As said before, my name is Sivan Sharabi, and I'm a master's student here in the urban planning program at the Technion. And today I'm going to present to you a little bit about my thesis, which focuses on evidence-based planning of street replanting. So I'm not going to do it as good as Elam did, but I did brought 4 pictures to help me convey the idea that the Israeli weather is characterized by intense heat during most of the year. And as can be seen here, Main Street in big cities in Israel all shows the same urban design failure. Streets were built without shade in mind, and in particularly street shade. Tree shade. To fix this, we first need to locate the climatic weak spots. Shade maps, which were developed in our lab, shows us where shade is missing and helps cities identify streets mostly exposed to heat. But here is the catch. While shade maps highlight shading conditions, they still don't tell us how many trees are actually missing. And this is the knowledge gap I am trying to fill. Unfortunately, we can't use a unified standard for tree crown areas. And as can be seen from these two pictures, trees develop very differently in different cities due to different planting conditions and tree management styles. Therefore, we need to analyze the actual state of trees in cities, in each city, and have a proper mapping of a tree crown area and the number of trees in each city to have a better understanding of the quality of their urban forests. The analysis of this kind of mapping showed me that different cities have different tree crown areas, and we need to take that into consideration. We need to tailor our approach to each city's reality. So to do that, we proposed two city-tailored quantification methods, a normative method based on tree crown diameter and an evidence-based method using actual street tree densities in well-shaded streets. While the first method is easier to calculate, it doesn't take into consideration the shading coming from buildings, therefore can possibly cause a higher estimation of the number of trees needed compared to the second method. In the normative method, we defined a design preference for tree crown overlap based on an average tree crown diameter and two rows of trees, one on each side of the street, to calculate the number of trees needed. In the evidence-based method, we are using correlation between street shade index, street widths, and street tree densities to estimate the actual street tree densities of well-shaded streets and use that to calculate the number of trees. As can be seen from our results, choosing different calculation methods leads to very different number of estimation of the number of trees needed to make a city well-shaded. As we assumed, the first method, based on tree crown diameter and different overlapping distances between tree crowns, have a higher estimation of the number of trees in streets. However, estimating a higher shade levels for the second method using street tree densities can lead to a more correlated, more aligned results between the two methods, highlighting the sensitivity of our results to different chosen planning assumptions and preferences. Ultimately, our goal is to develop a digital tool that will enable planners to define where shade is missing, to calculate how many trees are needed to fix the problem, and to set planting priorities, not only from planning preferences or assumptions, but also taking into account urban politics aspects like financial resources, feasibility, planting space, and social vulnerability. Thank you very much for listening.
Very much. Now we have our last presentation, and it is virtual because Serene finished his PhD and
Serene, can you speak?
He's abroad, I think in Barcelona, right?
Yeah.
Yeah. So lucky here in Barcelona. So we are here and listening 5 minutes of his presentation. And then we will have the commentary session.
Good afternoon, everyone, and shalom from Barcelona. I'm excited to share a glimpse into my PhD research, which aims to transform computational design decision-making, placing multi-species interactions at the center of how we shape our urban environments. Urban expansion takes up vast amounts of space, and in doing so results in habitat loss. As our cities become less hospitable for other than human species, we need new design approaches that treat other life forms as equal stakeholders. To me, Urban environmental intelligence means rethinking our basic understanding of the abiotic environment around us. Sun, soil, water, air, not just as data, but as part of an eco-logic that informs every design decision we make. Sustainability has long focused on human-centered goals, reducing energy, improving comfort, curating design aesthetics. But real environmental intelligence must also include the living organisms that we share our cities with. This is where multi-species design adds value. For example, plants already support our urban systems. They regulate thermal conditions, they improve air quality, and by understanding and leveraging their biological properties, we can design architecture that invites more mutual multi-species interactions. Plant functional traits gives us a common language. Traits like rooting depth and shade tolerance allows us to link plant species to environmental conditions. This lets us reimagine green infrastructure as ecologically informed and not just visually green. We already have the capabilities to simulate environmental data, such as soil distribution and shading conditions. But these tools often provide insights on how we could improve our lives. While important, this perspective is insufficient. Plant functional traits allow us to go beyond anthropocentric approaches. We can use them to approximate which areas on building geometries meet the abiotic needs of specific plants, and this makes the design process more inclusive of other than human species. This trait-based method allows for intelligent plant selection and distribution, tailored not just to climatic information, but to site or project-specific conditions. It makes ecological data actionable in the early design stages. From here, we can generate multi-species performance indicators. These are measures that help evaluate how a building's morphology could support ecological interactions. These indicators provide spatial insights that guide better design decision-making. As microclimatic conditions vary across facades, spatially explicit indicators like proximity or area clustering help us refine geometries that improve ecological outcomes. Small shifts in design decisions could potentially support biodiversity. More importantly, we can develop interdisciplinary collaborative processes with ecologists. Together, we can develop proxies like estimating how many plant species a building might support, or mapping vertical corridors that help connect fragmented urban habitats. Using parametric tools, such as the one developed in my research, we can embed these indicators into computational design workflows and allow for dynamic and iterative optimization processes that also capture ecological performance. Combined with our designer's intuition, these tools can support early-stage decisions driven by ecological intelligence, helping us prioritize both humans and other than human stakeholders in each design alternative. Urban environmental intelligence means redefining existing design processes as an ecological collaboration. It's not just about sustainability, it's ensuring that we can coexist meaningfully with nature, even in our densest urban spaces. Thank you.